from the beginning, our first object here we have is a sphere. And with the sphere, we will perform a horizontal cross section. In other words, we will cut this sphere in half using a plane, and then be able to view the shape of the cross section, which is that half of the shape that the plane is existing in. And so when we scroll up to the top of this particular shape and look down on it, we see that the cross section of a sphere is a circle. And the diameter of the circle will be different depending on the orientation of the cross section cut. When the cross section cut is high on the sphere, as it is right now, we have a smaller diameter of the circle. When I move the cross section cut lower into the sphere, closer to the center of the sphere, then we will end up with a diameter of the circle that will be larger. Next, we have an oblique cut. Oblique basically means diagonal cut. Diagonal cut of a sphere, since a sphere is the same dimension in every direction from its center point, a diagonal cut is going to produce the same cross section, a circle. Again, the size of the circle will be dependent upon the orientation of that plane as it's cut through the sphere. The closer that plane is to the center of the sphere, the larger the diameter. The closer that plane is to one of the ends of the sphere, the smaller the diameter of the circle. Our next cross section that we will see is a vertical cross section, again with our sphere. You'll notice that the vertical cross section is going to also be a circle. Doesn't really matter which direction you cut the circle or the sphere in half, the cross section will always produce a circle. Now I'll attempt to split the sphere in half and rotate the two pieces so that you can see what the sphere looks like when it has been cut in half. Those of you working with your Play-Doh during the cross-section lab should show a similar shape. You should have a half circle or a I guess a half sphere, semi-sphere after cutting the sphere in half. Our next shape is going to be a rectangular prism. And so on this rectangular prism, we will do a horizontal cut, and that horizontal cut will create a cross section that is a rectangle. Now as I tilt the cut and it becomes more of an oblique cut or a diagonal cut, you will still see that the cross section continues to be a rectangle. Now we have a full oblique cut from corner to corner. And as you can see, the cross section is still a rectangle. Trying to give you different perspectives on this because it helps for you to be able to see that rectangle within the rectangular prism. Now I'm working with a different orientation on the cut. So we're going to have a vertical cross section, which you will still see that the vertical cross section of a rectangular pyramid is also a rectangle. And again, I will split the two pieces of my shape in half, very much similar to what you should have when you have cut your Play-Doh in half. You should have two pieces of your rectangular prism that are split down the middle. And when I shift out the second piece, you can see clearly that the cross section is a rectangular shape. So now we'll transition into a triangular prism. A triangular prism will have a couple of different orientations. We're going to start with a horizontal cross section of the triangular prism, and as you can see, it creates a rectangular shape. And again, just like with the circle, the size of that rectangular shape will be dependent upon the orientation of the cross section. A cross section that is performed lower on this particular triangular prism will create a bigger rectangular shape. A cross section that is created higher, closer to the tip, will create a smaller rectangular shape. Now as I angle into a vertical cross section of this triangular prism, you will notice that this creates a rectangular cross section. Then we'll shift again to a different orientation. Now I have done a vertical cross section that shows you how this has a second option for a cross section shape, in which now we have a triangle. So we need to be careful to make sure that we differentiate how we are cutting our triangular prism so that we are familiar with what type of shape the cross section will be. Now my oblique cut cross section that is cut on a diagonal, you still see that we have a triangle in shape. Now I've used the software to cut off that other side so that we can see that triangular shape on the cross section a little more clearly. And you'll notice as I change the or angle the cross section even more, it creates some unique shapes. Just trying to give you a good visual of what actually takes place when a triangular prism is cut so that you can reference it. Naturally, you'll be doing some of these similar cuts with your Play-Doh in class, and so you'll have an opportunity to experiment with the potential options for cross sections. Our next shape is a cylinder. We'll notice that when we take a horizontal cut of a cylinder, we end up with a cross section that forms a circle. Now I will bring that cross section cut to a vertical alignment. And so a vertical cross-section of a cylinder produces a rectangular shape. And this is probably one you'll need to be careful with, because you'll need to look at your image carefully to determine the diameter across the circle or across the base of the cylinder. Because if the diameter is equivalent to the height of the cylinder, then your shape would actually be a square, which is somewhat what is represented right here. Next in our cross sections lab, we will take an oblique cross section, in which you'll be tempted to call this a circle. It's not really a circle, it is actually an ellipse. If you struggle to remember ellipse, I will accept oval as an optional answer, but our technical classification is an ellipse. An oblique cross section or diagonal cross section of a cylinder produces an ellipse. That one will be a little bit harder for you to see in the Play-Doh, especially since sometimes your Play-Doh being so small and conforming a little bit as you cut through it will tend to look more of a circular shape. Our next shape is a cone. We take a horizontal cross section of a cone, and you can clearly see that that's going to result in a circle. And again, the size of the circle will be dependent upon the orientation through the cone. So if I cut closer to the base, I will have a larger cross-section circle. If I cut closer to the vertex, the apex, then it will end up in a smaller cross-section circle. Now I'll start to transition that cut to show you a vertical cut on a cone, and that will produce a cross section that is a triangle. We won't do a whole lot with other options for vertical cross sections of a cone, but if you don't cut the cone directly through the tip of the cone, then you'll actually end up with what we call a parabola cross section, and that's not going to be a big focus until you get into some of your later high school geometry units. Now we will transition to our oblique cut or diagonal cut of a cone. And again, you will see the ellipse shape coming out. This one has a little bit more, I think, of a defined ellipse shape than the cylinder, but a lot of that is relative to the size of the original 3D shape. Here I show you the cone with the tip cut off completely. If I was using 3D printing, then that's what I would actually send to be printed from the 3D shop. Our next shape is a square pyramid. We scroll down a little bit so you can see the bottom of this pyramid, or the cross section of this pyramid. So you'll see that the cross section of a horizontal cut on the pyramid will produce a square. Again, the closer that cut is to the base, the larger the square will be created. The closer we get to the apex or to the tip of the pyramid, the smaller the cross section square that will be created. As we rotate our cross-section cut to show a vertical cut of the square pyramid, you should notice that the vertical cross section of a square pyramid is a triangle. You'll get the same cross section no matter how you cut vertically with the square pyramid, as long as you are keeping perpendicular to the flat surfaces. Now we're seeing an oblique cut of the pyramid. The oblique cut of the pyramid is actually going to produce a trapezoid. And so that's a unique one that we haven't seen yet. An oblique cut of a square pyramid will produce a trapezoid. Now I want to introduce something that's going to be very important for you on your quiz and test and even the final. The maximum number of sides for a cross section is equal to the number of surfaces on the original shape. And so since this square pyramid has 4 slanted surfaces and the one base, that would be 5, the cross section as we see it down here will have 5 potential sides to it. There's no orientation in which I can angle the cut that would create more than 5 sides, because the maximum number of sides to a cross section is dependent upon the maximum number of sides to the original shape. Now we're transitioning into a rectangular pyramid. So this will have a rectangular base. When I apply the horizontal cross section, you will see that the cross section of a rectangular pyramid is in fact a rectangle. Again, the orientation as the cross section is cut closer to the base will create a larger rectangle. Closer to the apex or the tip of the pyramid will create a smaller rectangle. Now we will tilt the cut. As we tilt the cut to an oblique cut, you can see again that just like the square pyramid, the rectangular pyramid will have a trapezoid cross section. Big difference here is that it will have longer sides to correspond with the longer length of the rectangular shape. And now as we transition, I will take this up to a vertical cross section. And from the vertical cross section again, you'll notice that it will create a pyramid. As long as my cross section is either parallel or perpendicular to the sides of the base, it will create a triangular cross section. Hopefully that's helped you to have a good view of cross sections. By way of review, the maximum number of sides for a cross section is equal to the maximum number of surfaces on the three-dimensional figure. So for a three-dimensional shape that's a triangular prism, maximum number of sides is 5. A rectangular prism, the maximum number of sides is 6.